Hi guys, today's lesson is the first one we're going to do in Unit 4. So Unit 4 is all about oscillatory motion, so things that oscillate back and forth, and mechanical waves. And we're going to jump right into wave theory today. So a wave, by definition, is the regular transportation of energy without the permanent displacement of matter. So if you think about a wave in the ocean, the water goes up, it goes down, but it isn't permanently moved from one place to another. It goes back to where it started. Or if we look up here at this picture of the guy using the ropes in the gym, the ropes go up, they go down, but they ultimately come back to where they started to. So the big thing here with this definition would be that in science, we're always talking about what's happening to the energy in a wave. So that's where our focus is. So, a few things to know. Waves are regular because the particles which make them up oscillate in simple harmonic motion, returning to their equilibrium positions. So, simple harmonic motion was 4.1 that we didn't go through, but it's just something that does the same thing over and over and over again, like swinging on a swing set. You go back and forth and back and forth. Waves transport energy, and it can be a number of different types of energy. So you can have waves that transport heat, light, sound energy, energy of water when you're thinking about actual waves in the ocean, and lots of other types as well. So waves don't displace matter or move it permanently, as the particles eventually are going to return to what we call equilibrium. Two main types. We've got mechanical waves. That's what we study in Physics 20. So anything like a water wave, a sound wave, a wave through a slinky or a string or a spring. And they need some kind of medium to travel through. Like waves in the ocean travel through water. Sound waves travel through air. If I'm using the ropes at the gym, it travels through the string or the rope itself. Electromagnetic waves are the second type that we'll study in Physics 30 if you take that course. And we study things like light waves, radio, TV, satellite rays, microwaves, UV waves. These do not need a medium, so these waves can travel through the vacuum of space. So we use what's called a sinusoidal curve to draw waves, and this is something that you'll study in detail in Math 30-2 or 30-1. So a sinusoidal curve is basically if you were to put in your calculator sine x in the graphing position and you were to change the window so that it was big enough to see, you would get this wave shape. And what happens is the wave goes up, it goes down, it comes back to equilibrium. The green line that I've just drawn is one wave. If I was to pick that wave or wavelength up and move it over, it literally makes the pattern go again and again and again. Okay, that's what we see happening with waves. Now, this wavelength in our equations in this unit is going to be given by lambda. So I'll draw it out by hand. It's a Greek letter. It kind of has a little hook at the top and goes down and then has a little part like that. So again, this is lambda. And this is going to represent the length of one wavelength. Now, some of the terminology that we use in science is a little different than what we might use in math. In science, we call the top a crest and the bottom a trough. In math, you can imagine these would be called the maximum and minimum points. And then this word is the same in science and math, the amplitude. So that's from this middle line that runs through the wave, the equilibrium line, to the very, very top. And I'm just going to call that A for amplitude. And that's going to be exactly the same. Waves have this symmetry going on where the amplitude down to this trough is going to be exactly the same. And this is the same amplitude, this is the same amplitude. All right, so This lesson is just a whole bunch of terminology so that we're prepared for the next lesson. Equilibrium was that line that is the initial position of the wave. If all of the energy was to stop, the wave would go back to that equilibrium position. So if you think about a wave pool, like going to West Ed and swimming in the pool is usually at equilibrium. And then when they turn the wave machine on, you've got those crests and troughs. And when the wave machine ends, everything goes back to equilibrium. The crest is the portion of the wave that's above equilibrium. The trough is the portion below. Amplitude between equilibrium and the very top, the maximum or the minimum. Wavelength is the distance between two repeating parts of a wave, and we use lambda to denote that. And the units for wavelength, just like other lengths that we would use in physics, is going to be meters. Now, it's worth going back and showing you another wavelength. It doesn't necessarily have to be this green shape that I drew. One wavelength can also be from, say, a maximum to a maximum. If I pick the blue part up and repeat it over here, I'll get the same repeating pattern over and over and over again. So you can imagine there's lots of different areas where I can draw one wavelength, maximum to maximum, minimum to minimum. I could even go, running out of colors here, but I could go part way like here to here, the same location on the next bit of wave. All of those are one wavelength. If you pick them up and like copy and paste them over, they're going to keep making the same pattern. Pulses are the individual crests and troughs, and then a wave train is a collection of pulses. So if we were in school right now, we'd get a bunch of these super long slinkies that we have. Two people would hold it, stretch it out, and then you would send pulses through the slinky, and you would look at what happens with the waves. If you send multiple pulses, so you lift your arm up and down multiple times with the slinky, you're going to be making what's called a wave train. So we're going to study two types of wave motion in Physics 20, transverse and longitudinal waves. So the definition is kind of confusing. I have a little animation to show this. A transverse wave is a wave where particles vibrate in a direction perpendicular to the propagation of the wave. That's a lot of big fancy words for this. So see how this wave is moving from left to right, but the blue dot goes up, down. That's perpendicular to the direction the wave is moving across, and the matter moves up, down. The longitudinal waves do this. See how the wave went left to right, and the dot also went left to right. So that's the difference there. Transverse, the dot goes up and down while the wave moves across, and longitudinal, the wave's moving across and the dot also moves across. So a couple examples, transverse, could be waves in a string. If you were doing the slinky activity in class, that would be transverse. Ripples on water, electromagnetic waves, and literally the wave if we ever get to go back to live sporting events again. Longitudinal waves are moving left and right, and then the wave moves left and right, and the particles move left and right. So this is sound waves. Longitudinal can be made up of high particle density areas, so compressions, and low density areas or rarefactions that we look at mostly in Physics 30. If we have both, earthquakes are usually an example of both transverse and longitudinal waves. They can be quite damaging. So that brings us to the end of this lesson. Just a whole bunch of terminology about waves for you to know. We're not going to do pulses in a string because we're not at school, so you can get rid of that. You can read that activity and see what we would have done in class with the slinkies. And if you have a Slinky at home, by all means, go ahead and try the activity. But really, your assignment for this lesson is just to read 401 to 410 and familiarize yourself, be able to use this terminology before we get into the math. Let me know if you need any help.